Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Transcendental Functions, Part 3, Logarithms and Exponentials with a focus on sketching and also derivatives and integrals. So hopefully you remember from your past experience talking about parent functions. A parent function is just the basic graph. And so here we have y equals e to x. This will represent our exponential parent function. So this would basically hold true for any base, but we're going to focus on base e. This is the one you'll most likely face in Cambridge questions. And also y equals ln x will represent our logarithms. Again, it could be any logarithm, but we're going to particularly look at ln, the natural logarithm. So these are the parent functions, meaning what the basic graph looks like. And then this formula in the blue is what it looks like if it's expanded and has some transformations in it. So let's look at our exponential function first. When you draw a curve, I like to call it 3 points of reference. When you're graphing a curve, you need 3 points of reference to make a sketch. Now we're talking about sketching, not a full detailed graph. So it just has to get the general shape and the general location. You're not too worried about really accurate graphing here. So we're just talking about a quick sketch. So with the exponential function, one of the features that you have is what's called an asymptote. And in this case, it's a horizontal asymptote. Now, what an asymptote is, it's kind of like an imaginary line that your graph cannot cross. And we don't really have time to explain fully the nature of asymptotes, but let's just call it, it's kind of like a fence. A fence is something that divides a yard or something, or is on the border of a yard. And you can come up and go close to the fence, but if you run into it, it keeps you from, going over the line. So that's what an asymptote is. It's kind of like a fence. It's like an imaginary line that prevents your graph from going across it. So the reason why there's a horizontal asymptote is because of our restrictions on the base. Remember, a base in an exponential has to be greater than 0. So if you have a positive base, then no matter what the exponent is, you're always going to get a positive number. You're not going to get 0, you're not going to get negative. So because y will never be 0 or negative, then we have this imaginary line here that our graph will not cross. That counts as one of your points of reference. So when we talk about 3 points of reference, you just need, it means a referral point, not necessarily an actual coordinate point. So this fence is 1 point of reference, and then we need 2 more points. Well, the easiest point is when x equals 0 on the y-axis. When x is 0, any base to the 0 power is 1. So it should cross at 1 on the y-axis. That's an easy point. Now we have 2 points of reference. All we need is a third point. For that one, you can actually calculate it on your calculator. Just pick some other value of x, plug it into your formula, and you get your third point. So the asymptote, the 1, and then your third point, that's your 3 points of reference. Exponentials usually start close to the fence, goes up through the 1, and then continues up in an exponential fashion from there. Now we get into the expansion. So the expansion can be a little bit tricky, but to help you, notice that our origin is right here. And so basically the H and the K are translations. The h shifts our graph left and right. It's connected to the x. The k shifts the graph up and down. And if you subtracted it to the other side, it would be like a y minus k. Okay, so the k is actually comes from your y variable, and it's what moves your graph up and down. The h is attached to the x, it moves the graph left and right. So because the k has already been moved to the other side, we've already changed the sign. So for the plus k, you don't change the sign anymore. If it's positive, it moves up. If it's negative, it moves down. The h is still attached to the x, so we need to change the sign. Whatever value h is, you're going to do the opposite. So if it says minus 3, you're going to add 3. If it says plus 3, you're going to subtract 3. Okay? So you change the sign for the h, you keep the sign for the k. What you want to first do is find your new, I call them like your new set of axes. So x prime and y prime. So it moved over on the x-axis to a positive h, moved up on the y-axis to k. Where those cross, that's your new origin. So this k is also your horizontal asymptote. So that's your first point of reference. The a, remember we said anything to the 0 power is 1. Well, if this becomes 1, then 1 times a is then a plus k. So from the k, you go a units up. So now you're at a plus k. That is the point on your new y-axis that you want to put the dot. That's this dot 1 here on the original becomes the dot a plus k on your new y-axis after you've shifted it left or right. You don't always have a left or right shift. Sometimes you have one or the other, and maybe you have neither of them. But so if you have neither, you're just right back at the origin again. So make your h and your k, where those cross, that's your new origin, go a units up from there. So that makes it a plus k. That is your second point of reference. And then again, just pick a third point and plug it into your equation and plot it. And that gives you your curve. Again, you start close to the fence. Over here on the left, you go up through the point on your new y-axis, and then you continue up in the exponential form through your third point of reference. Don't forget, if you have negatives, and again, I hope they don't do this to you, but just in case, if you have negatives on your variable, it makes you flip across an axis. If you have a negative on your y, it's going to come across and end up on your a. Because remember, they want y to be the subject. So if the negative started on the y, divides to the other side, and you end up with a negative a. So that means if the negative started on the y, you flip across the x-axis. Well, this is your new x-axis, so that would mean that your graph you would have some dot like here, and your graph would go something like this. Okay? So negative on the a means your graph is going to flip across your x-axis. And if your negative were on the x, then it's going to flip across the y-axis. So it would be more something like this. Okay, so this is a negative on the y, which actually means it's going to be on the a. Put it like that. And this one would be a negative on the x, means it flips over your y-axis. So start with your translations, get your origin, put your a value in from there, and obviously if it was negative a, you would count down a units, and then find your third point by plugging in just some random number out here to the right of your h, and draw your graph. Okay, now let's look at ln. Here is your parent function graph for y equals ln x. Remember again, here we have what's called a vertical asymptote. So again, it's an imaginary line our graph can't cross. And this vertical asymptote is because of our argument. Remember, the argument of a logarithm cannot be 0 or negative. So since the x cannot be 0 or negative, then that means we're not allowed to go over into that section of the graph. Unless, of course, it's translated left to right. This imaginary line can be moved left or right, but this is your parent function. Now with the expansion, notice again the translation values of h and k. Again, remember the k started off over here as a y minus k. Because we make y the subject, k got added over here, and the h is still attached to the x. So just like we did here, we made our new x and y axis based on the h and k translation. We'll do the same thing here. You do the opposite of h, so that moves it in the positive direction. The same value as k moves it up. Remember, again, it can move up or down, left or right. You follow the same sign as k, the opposite of h, and that creates for you your new origin. And then from there, you just go 1 unit to the right. Notice this is 1 unit to the right of the asymptote. You go 1 unit to the right, so whatever your h is plus 1, and you put a dot there. So remember, this affects your up and down, not your left and right. So if your, and the A is a multiple of it, it also affects your y value, it doesn't affect the x. So this plus 1 here is just like this, it's all on the x part, it's not affected by the A or the K. So this is 1 across, you just go 1 over. So the fence, that vertical asymptote is 1 point of reference. From your new origin over 1 unit, that's your second point of reference. And then you need a third point that you can just plug in on your calculator and find. That's your third point of reference. Your logarithm graph usually starts down close to the fence, up through that dot that you've created on the x-axis, that's 1 unit away from your asymptote, and then goes in a curved fashion off to the right through your third point of reference. So now again, let's look at negatives. If your negative was on the y and divides over to be on the a, so a negative on the y flips you over the x-axis. So if you flipped over the x-axis, you'd be going like this. And if you had the negative on the x, means you flip over the y-axis. Flipping over the y-axis would put you 1 unit on this side. You're 1 unit on that side, so you'd be 1 unit on this side, and your graph would start down here and go up something like this. It'd be kind of the mirror image of this one, but over here. So a negative on the x flips you over the y-axis, a negative on the y, which actually shows up on the a, flips you over the x-axis. So that's kind of in a nutshell how you do the sketching. And if you just pay attention to a few of those details, how to get your first, second, and third points of reference, then you can do it rather quickly without having to do a lot of XY plotting. So let me set up an example for that. Okay, let's look at our first question here. And you can see the code up here at the top from Winter 19, paper 33. And it says, by sketching a suitable pair of graphs, notice it says pair of graphs, show that the equation ln of x plus 2 equals 4e to the negative x has exactly one real root. So it wants us to sketch a pair of graphs. So let's go back to our board. Here I've drawn it here. On the one side we have a logarithm, natural logarithm ln of x plus 2. On the right-hand side, we have an exponential, 4e to the negative x. And it says it wants to show that there's one real solution. In other words, they intersect at one point. So we'll graph them both separately and see that where they intersect. So if we take this one, remember it's the h supposed to be x minus h. We need to change the sign. So instead of plus 2, means our vertical asymptote is moving back 2 units. So 1, 2, we have a vertical asymptote. There's no k value, there's no outside value to shift it up or down. So that means our x-axis hasn't moved. And so from our horizontal or vertical asymptote, we come over 1 unit on the x-axis, and remember it wasn't shifted up or down, so right on the x-axis, that is our second point of reference. And then we need another point, so we could plug in a 0, and if we plug in a 0, ln 2 is just in here somewhere. So if we plug in here's a -1, here's 0. If we plug in a 0, we get ln 2. Ln 2 comes out to 0.69, so almost 0.7. And so remember, your graph starts down here close to the vertical asymptote, goes up through the x-axis at the point that we put on it, and then out through the third point of reference. So see, that didn't take a lot of work. We only looked up one value. The other two we figured out from here. Now for the exponential. First of all, the h and k, there's no h and k. So that means our horizontal and our vertical asymptotes have not changed. So we have a horizontal asymptote at 0. So there's no k value to lift it up or down. There's also no h value to shift it left and right. So in other words, we're right on the y-axis here. Here's our x-axis, here's our y-axis. And so from our origin, we go up a units from the origin or from the k if it has a k. And so here's 1, 2, 3, 4. So that's a point there. And normally it would start from the x-axis this way, from the asymptote, and go up. But notice there's a negative on the x. So the negative on the x means it's going to flip over the y-axis. So instead of going up like this, it's going to go down. So it's going to start from over here, and it's going to come up this way. And actually, here's 1 point of reference. Here's 2 points of reference. You don't really need a third point of reference, but you could put it in if you wanted to. You could pick -1, or you could pick any of these numbers out here. What's important is that you've demonstrated that there is one root. There's one real solution to this problem, and it's right at the point of intersection there. So that's the kind of sketching that you'll be doing. Again, you need to understand reflections. You need to understand translations, move left, right, up, down, reflecting it over one axis or another. So it's kind of a limited exposure. They don't ask a lot of sketching for logarithmic or exponentials, but it's worth keeping in mind Your translation H and K things you've worked with before on parabolas, and you'll get also your trigonometry. In trigonometric graphing, you'll have it there as well. So once you get used to it, you just have to apply it to the different graph types. Okay, now what I want to do is set up for derivatives and integrals. Okay, for derivatives and integrals, you've already learned derivatives and integrals for algebraic terms in polynomial form. So polynomial form means you have a function of x and you have like, x cubed plus x squared plus x plus something like that, where it's polynomial form, and you've learned how to derive or integrate one term at a time. So that is with algebra. Now we're moving on to derivatives and integrals with exponentials and logarithms. Again, specifically looking at our natural base e and our natural logarithm. So there are other derivative and integral formulas that go with other bases and with different logarithms, but for Cambridge, they focus on the natural logarithm. So with y equals e to the x, it's very interesting that, remember, derivatives represent slope and integrals, the main application is area. So again, we use y prime and sometimes dy dx. You need to know when to use differentials and when you don't have to. I'm just putting y prime right now just to show that we've taken the derivative of y. And then on the right-hand side, we're showing the differential. So the derivative of y in this equation, y equals e to the x, is also e to the x dx. The dx means you have to take the derivative of the exponent, whatever that happens to be. And so notice the derivative is the same as the original function. This is what makes it a special function, and that's one of the interesting characteristics about this natural e, this 2.72 rounded to 2 decimal places. And that is the y value at a particular place at x is equal to the slope at that same particular place. So the value on the y-axis is equal to the slope as you go around the curve. So it makes it quite easy to do the derivative. Derivative of e to the x is just e to the x, but don't forget to do the dx, which is the derivative of the exponent, especially if your exponent is expanded. Then for integration, integration is just going backwards. So the integral of e to the x dx would then just be e to the x. And don't forget the plus c if you do not have bounds of integration. So this one is quite easy. Just don't forget the dx if you're going in the forward direction, and don't forget the plus c if you're going backwards. Then for ln y equals ln x, the derivative of ln x is 1 over x dx, where the dx is the derivative of the argument. So if your argument is expanded, you need to do the derivative of the argument after you do the 1 over x, which is 1 over the argument. Now, going this way, by the way, these formulas are in your formula sheet, so please make sure if you have any questions when you're working a problem, refer to your formula sheet so that you don't get confused. This one can be confused when you go backwards. Why? Well, going forwards, it's obviously a logarithm, and you'll probably remember that it's 1 over x, or you look it up in the formula sheet. But if you're going backwards, if you're integrating 1 over x, it can be a little confusing because it looks algebraic. So you start with 1 over x and you have to integrate it, and you're like, you don't see the logarithm. So it's not, it doesn't get into your head that it's a logarithmic integration. And so you might treat it as algebraic. You bring the x up to the -1. Well, what's your formula for the algebra integral? Well, you add 1 and divide by the number. So if we add 1, that gives us 0, and we can't divide by 0. So if going backwards can be tricky because it looks algebraic, but it doesn't work. So be careful of that. Try to recognize that 1 over something, that fraction, 1 over x, or any kind of a fraction as potentially a logarithmic issue, especially when the exponent is 1 on the bottom. So the integral of 1 over x dx is actually ln x. Now notice, instead of having the parenthesis around the argument is now an absolute value. I don't really have time to really explain that. It hardly will affect anything that you do with Cambridge, although if you're double checking your answer, if you happen to have a negative argument, this makes sure that it turns positive. But technically, you could probably get away with putting parentheses for the most part. It might catch you once or twice, but technically you're supposed to put absolute value on your argument for a logarithm when you're coming out of an integration situation. So ln absolute value x plus c, again, because there's no bounds of integration. Now this pattern, this algebraic pattern, notice the derivative of x is 1. If you go back to your algebraic derivatives, the derivative of x is just 1. So we've got a pattern that you can look for. When the numerator is the derivative of the denominator, that is going to turn into ln absolute value f of x, whatever that function is on the bottom, plus c. So for example, if you had x squared plus 5x on the bottom, that would be 2x plus 5 on the top. And if you are integrating this, you should recognize, the top is the derivative of the bottom. The bottom is x squared plus 5x. The top is 2x plus 5. That's the derivative of this. If the top is the derivative of the bottom, then that is going to equal ln of the bottom plus c. Okay, so this pattern is an important pattern to recognize. Now, we don't have a lot of examples that we can actually work through because after transcendental functions, the next unit is going to be derivatives. And we're going to expand from being able to do polynomials where you did one term at a time. We're going to expand into products and quotients. So multiplication of terms and division of terms, whereas before you've only been able to do addition or subtraction of terms. Now these products are going to be products of two different terms. One could be exponential, one could be algebra, or one could be logarithmic, and one could be trigonometric. So you can have a lot of different combinations with products and quotients. And so what's going to be important as you get into the product and quotient rules is that you can do the derivative of the individual parts. You can still do the derivative of an algebraic term. You can do the derivative of an exponential or of a logarithmic term. And that way, when we put it all together into the product and quotient rules, then you will be able to be successful and you can focus on the mechanics of the rule because you already know the derivatives of the parts. Okay, So what I want to do is just show you really quickly. I'm going to set up a few questions that are in that product or quotient setup, and we'll just look at the individual parts without carrying out the whole rule, which we haven't learned yet. Okay, really quickly, I'll just show you what I'm talking about here. Here's two different questions that you'll be getting to in the next unit on derivatives. Both of these happen to be quotient rules. They could be a product as well. You could have e to the 3x times tangent 1/2 x. Notice one of them is an exponential function, one is a trig function. Down here in this quotient, again, it could be a product like x times ln x. In this case, it's a quotient, ln x squared over x. So we have a logarithmic and an algebraic. So again, we're not doing the quotient rule. What I want to just focus on is this exponential, e to the 3x, and this logarithm part, ln x squared. You already know how to do the derivative of x. The derivative of x is just 1, and you have not yet learned derivatives for trigonometric functions. We'll get into that also in transcendental functions, but after we've covered logarithms and exponentials. So that's coming up in the following videos for that. So we're focusing on e to the 3x and ln x squared. So here we're doing derivatives. Here is our basic formula. E to the x is e to the x dx. Now we're given e to the 3x, and we want to derive it. Okay, so we're going to take the derivative d dx of e to the 3x, and we're going to get e to the x, which is e to the 3x, dx. The dx is the derivative of your exponent, and the derivative of 3x is 3, so this equals 3e to the 3x. So the derivative of e to the x is e to the x. Whatever x is, it stays the same. Then you have the dx, which is the derivative of your exponent part here, which is the 3, and it gives you 3e to the 3x. Now on the logarithm here, if we do d dx here, we have an exponent. So when we have an exponent and inside we have our function, we do the exponent first. Our exponent follows kind of like what we did in algebra. We multiply it to the front. We subtract 1. So that just gives us 2 ln x. We're doing derivatives, so we can use the parenthesis. The absolute value is for integration. So multiply the 2 to the front, subtract 1 gives us a 1 as our exponent for our ln x. And then we need to do the derivative actually of the inside, because that was just the exponent part. So do the exponent part first. Now we need to do the function. So the derivative of ln x is 1 over x. And then we need to do the dx, which is the derivative of the argument itself, and it's just x, so the derivative of x is 1. Okay, so first we did the exponent, second we do the function, third we do the argument. So up here, first you do the exponential, and then you do the exponent itself. That's the dx part. So this one, because it has this outer exponent, we had 3 parts: exponent first, function second, argument last. So this gives us an answer of 2 ln x over x for that particular part. Okay, so that's all for now. That's sketching and derivatives and integrals, with a little bit of a taste of how you will see it in future questions, as well as hopefully a better understanding how to do a quick sketch on exponential and logarithmic functions. As always, thank you for joining me in the Zoom room. Hope to see you again next time as we move on into our trigonometric functions.